Good morning, and welcome to the IEEE PELS webinar series. I am Mike Markowitz, and on behalf of the Power Electronics Society, I would like to welcome you again, Custom Silicon, and let me tell you how. Presented by Alex Lidow and David Reusch. During the presentation, if you have any questions, please submit them to me via the chat box. There will be a brief Q&A session after the presentation. Again, I would like to thank you for joining us this morning, and with that, Dr. Alex and David.
Thank you, Michael, and thank you, everybody, for attending this webinar. My name is Alex Lidow, and I'm Chief Executive Officer of Efficient Power Conversion, and I'm joined with David Reusch, who is our Director of Applications Engineering, and we're going to tell you about GaN crushing silicon in the world of power conversion. So let's get started. We're going to tell you first how eGaN FETs work. eGaN FETs are enhancement mode field effect transistors made in gallium nitride grown on top of a thin film of silicon. They have the opportunity to work 1,000 times better than silicon power Mosfets. And today, in our early generation of devices, we're running about 5 to 10 times better than silicon, and we'll show you how and why. Then we'll get into hard switching DC to DC converters. One of the most popular forms of power conversion. David Reusch will walk you through some very interesting examples of high-efficiency point-of-load converters and envelope tracking buck converter. Then we'll take you into resonant DC to DC converters. The two examples that we'll give you are a bus converter, which is a very popular type of a DC to DC converter used in servers and telecommunications equipment. And then we'll get into a new topology, the ZBS Class D topology for wireless power transmission. And finally, we'll take a look into the future. Where is this marvelous new technology going? It's just begun a journey, and it's already crushing silicon. Let's see how far we can go with it. And then we'll take some of your questions, and hopefully we'll give you some answers. I started making power transistors in the 1970s, and I heard the same thing over and over again. What do people want in a power transistor? They want a device that has lower on resistance, because this gives you less conduction losses in your circuit. Lower on resistance is always perceived to be a better thing. They want a device that's faster. Faster devices have less losses, particularly in switching losses. They want a device that has less capacitance, because less capacitance means less losses charging and discharging the devices. It can also mean less power required from the driver. They want a device that's smaller, because smaller takes up less space on the printed circuit board, and that board space is the most expensive real estate in the world. And then, of course, everybody wants lower cost. No matter how good a device gets, these will still be the 5 key areas for improvement. So let's make a comparison here on very fundamental grounds between silicon, silicon carbide, and gallium nitride. And I'm going to start with the crystal properties of these 3 materials to show you why gallium nitride is a superior choice. First of all, silicon. And we're going to look at 3 characteristics. The band gap energy, which is in essence related to the force it takes to break the bonds between the silicon atoms in the crystal. We'll look at the breakdown electric field. That's the amount of energy it takes to pull one of the electrons off the bond, and it's very closely related to the band gap energy. And then finally, the electron mobility. And that's how easily the electrons can move through the crystal, how sticky they are as they scoot around inside the silicon. And let's compare these with gallium nitride and silicon carbide. As you can see, the band gap energy in gallium nitride and silicon carbide in both cases is about 3 times higher than silicon. That means that these bonds are much, much harder to break. And as a result, the breakdown electric field, the amount of electric field before the electrons get stripped off of the crystal lattice, is 10 times higher in gallium nitride and in silicon carbide compared to silicon. What that means is you can bring 2 electrodes 10 times closer together with the same voltage before they will arc over or avalanche inside the device. That's very important. because what it means is you can ultra miniaturize your device. The closer you bring the terminals together, the smaller your features, and also the less resistance there is between the terminals. And there's a third effect, and that is you can also pack more charge in between those terminals before they arc over. The net effect of a 10x increase in breakdown field is a 1000x possibility for improvement in resistance per unit area. And then finally, electron mobility. As you can see, silicon has a very high mobility, 1,500 centimeters squared per volt second. Silicon carbide, quite a bit worse. But gallium nitride, the best of all, at 2,000 centimeters squared per volt second. And that's because of a unique characteristic called a two-dimensional electron gas, which we'll discuss in just a minute, which allows the electrons to move faster and easier throughout this crystal. The translation of these characteristics can be shown in a graph like this. On the vertical axis, we have the on resistance for a 1 square millimeter piece of active area in silicon carbide, gallium nitride. And on the horizontal axis, we have the breakdown voltage that you can achieve. Now remember, the terminals can get closer and closer together as you get higher critical fields. As you have higher mobility, you get less resistance. And this is the result. The silicon limit is up at the upper left of this graph. And as you can see, silicon carbide is about 100 times better. Gallium nitride about 1,000 times better. And that's really where we can go with this. Today, devices are 5 to 10 times better, but we are just at the beginning of the journey. So how does this all work? First of all, there's this magic, and that is the two-dimensional electron gas, shown here as the little circles of electrons between a source on the left and a drain on the right. Gallium nitride is piezoelectric. What that means is if you squeeze it and push it and torque it, it will actually generate a small electric field. And one way of doing that very efficiently is grow a crystal on top of it that has a different lattice constant. And aluminum gallium nitride is a very convenient one. What the aluminum gallium nitride does is it squeezes the top of the crystal. Very, very, very thin layer is squeezed, and that generates an electric field. And in that electric field, it attracts electrons. And if you make an electrical circuit, as shown here, you can conduct a lot of current in a very small piece of crystal, and very efficiently. So we can take that and make a device out of it. And one of the ways that we do that is if you put another electrode between the aluminum gallium nitride and the gallium nitride and apply a negative field, a negative voltage to the aluminum gallium nitride compared to the gallium nitride, you can deplete away all those electrons. They go away. So now you have a device that can turn on and turn off, but it's depletion mode because it takes a negative voltage to turn this off. So let's build a device out of this. This is a cartoon of a cross-section of a fairly generic device. Almost all gallium nitride transistors you see today are built like this. It's called a lateral device because you have your aluminum gallium nitride on top of your gallium nitride to create this two-dimensional electron gas. And on the top surface, you have a gate, a source, and a drain electrode. The gate is there to take away the electrons, and the electrons will flow between the drain and the source. You can also put a protection dielectric on top of it and actually seal this entire device off. That becomes important when we're talking about packaging. This is the foundation of a depletion mode device. Now, can we make this into an enhancement mode device? And the answer is yes. And Efficient Power Conversion Corporation, EPC, conquered that challenge about 4 years ago. So let's look at this cartoon of that cross-section device that we had before. In EPC's case, we've actually created a gate electrode shown in orange that is made out of a special crystal that automatically depletes away the electrons. And therefore, the device looks like this in its resting state with no voltage applied to any of the terminals. However, if you apply a positive voltage to the gate terminal, you suck electrons up there and complete this circuit. And that's the way an enhancement mode device works. There's kind of a neat feature about enhancement mode devices, and that's that they work in both directions. And that creates the equivalent of a body diode like you have in a Mosfet. So here's that same device, and if all we do is apply a positive voltage compared to the drain electrode, we again suck the electrons up and complete the circuit. So you can actually conduct in both directions. What does this look like in real life? Here's a cross-section of an actual device made by EPC. You can see in here there are 3 metal layers, tiny gates down there in the lower left, drain electrode, a source electrode. These are made with sub-micron feature sizes. And this device is manufactured in a standard low-cost silicon foundry in Taiwan. And we build these parts side by side next to CMOS wafers. And as such, we can take advantage of the very low-cost infrastructure that's been built over many years in the world of silicon. EPC has a whole family of devices. Right now, there are 5 die sizes that you can see from the left to the right, big to small. They range from 200 volts down to 40 volts, from 33 amps DC all the way down to a couple of amps. These devices were first introduced in March of 2010, and they've been making a big dent in the power conversion market since then. Recently, EPC introduced a new family of ultra-high frequency EGAN FETs. These devices have significant gain all the way up past 2 gigahertz, breakdown voltages from 40 to 100 volts. You'll see some design examples with these at very high frequency switching applications. And you can buy all of these parts online. They're all in stock at DigiKey, and you can get them delivered overnight. So what about the electrical characteristics? We showed you the physical properties, and there's some really remarkable advantages in gallium nitride compared to silicon. One is because of the way EPC made this enhancement mode gate out of a crystal instead of out of an oxide, it actually is extremely stable with temperature. And in this graph, we're showing you the threshold voltage of a device normalized to 1 volt at 25 degrees C. And the threshold voltages represent the vertical axis and the junction temperature on the horizontal axis. You'll see the red line. That's a Mosfet. So if a Mosfet voltage is, say, 1 volt at 25 C, at 150 C, it would be 0.6 volts. If it were 2 volts, it would be 1.2 volts at 150 C. In contrast, gallium nitride FETs are essentially flat. And therefore, you don't have to have a high threshold voltage at room temperature to maintain high noise immunity when the device is running hot. Another very important aspect, perhaps the one that caused most of the engineers that are early adopters to buy these products, is the amount of charge it takes to turn the device on or off. That's called the gate charge. And you can see a comparison here between 2 devices, which are very, very similar in electrical characteristics. One is from Infineon. It's an 80-volt, 5 milliohm part. The other one's an EPC 100-volt and 5.6 milliohm part. And on the vertical axis, you can is shown the gate-to-source voltage, and on the horizontal axis, the amount of charge it takes to achieve that voltage. And this is a very typical curve. You'll find it on data sheets, and has 3 regions. The first sloping one on the farthest left is the charge that is required to get the gate voltage up to threshold, and then up to the point where it changes the output state from blocking voltage to conducting, or from conducting to blocking. And then you see a flat line, a horizontal line. That's called the plateau voltage, and that's the gate to drain charge that it takes to change the state at whatever voltage is applied. And then you have another lateral line, and that one is the overdrive, the charge that you apply just to get the gate to a higher voltage to maybe get a little bit more enhancement of the channel. You can see a comparison here between the Mosfet, the best that we could find, versus EPC 2001, and obviously there's a significant difference, maybe 8 to 1, between these 2 devices in terms of the amount of charge it applies. That translates into lower drive power, and most importantly, much faster switching transitions. One of the characteristics of an EGAN FET that we talked about is the reverse diode, which is actually just turning on the channel. And this graph shows the characteristics of that reverse diode compared to a Mosfet. Here's one area where there's a disadvantage compared to the Mosfet. On the horizontal axis, you have the source drain voltage, and the vertical, the source drain current. They both look like diodes. The EGAN FET is on the right, the Mosfet on the left, and you can see the forward drop of the Mosfet is significantly lower. And in fact, as you go up in temperature, the forward drop of the diode gets lower. In the case of an EGAN FET, the forward drop of the diode gets higher with temperature, and it starts off at a higher value. And basically, this is a disadvantage of the FET, but it's very much offset by the fact that the diode in the EGAN FET is majority carrier electrons that can be turned on and off instantly. Now, MOSFET, they're minority carriers, and they have to be collected back into the source and drain electrodes. Therefore, you have a reverse recovery charge in a MOSFET. In an EGAN FET, the reverse recovery charge is 0. In many circuits, the speed of that circuit is limited by the amount of time you have to sit there and wait for that diode to recover. In an EGAN FET, there is 0 recovery time. That allows you to go to much higher frequencies with your switching circuits. So let's compare in another way with a power MOSFET, and this I'm going to use a very generally applied figure of merit. It's called the conduction figure of merit. And if you want to compare technology, it's a pretty good start. It doesn't necessarily predict all aspects of performance, but it's a good start for looking at how one technology compares to another. On the vertical axis, I have the gate charge. That's as we saw before, that's the charge it takes to change the state of the device from on or off to on. On the horizontal axis, we have the on resistance of the device. If you want a lower on resistance device, it usually has a higher gate charge. And therefore, multiplying these two together can be represented as a figure of merit. If we plot them independently, like on this chart, you can see the actual results right away. The small dots are 200 volt silicon power MOSFETs. The best are the farthest to the left, and as you can see, they scatter about. This line represents EPC's second generation 200 volt EGAN FETs, and you can see that it is far away from the very best power MOSFETs that you can buy. As a matter of fact, a 7x improvement. You can go to a different voltage. Let's look at 100 volts, blue dots, and the difference is 5.5x. Let's go to 40 volts, green dots, and the difference is 3x. So you can see that there is a substantial improvement, no matter what the voltage, between your silicon devices, the aging power MOSFET, and the brand new EGAN FETs from EPC. So, just to summarize it, then I'm going to turn it over to David to give you some design examples. EGAN FETs are superior to MOSFETs in almost every way. In green, we can see the areas where the EGAN FET is superior. Like a MOSFET, you have I²R conduction losses, and they're superior. Capacitive switching losses, superior. Gate drive losses, very superior. V times I switching losses, that's the power loss during the switching transition. Again, very, very much better. Not like a MOSFET, the EGAN FET has high reverse conduction losses. And we'll show you how to avoid using the diode in a way that penalizes your circuit for that. However, there are no body diode reverse recovery losses. And that makes it a much, much better device to use in high-frequency switching applications. So let me turn it over here to David Reusch, our Director of Applications Engineering. He's going to take you through some design examples, and we'll get back and look at the future.
Thank you, Alex. So now I'm going to talk about give some design examples and show the benefits of in-circuit performance that's offered by enhancement mode gallium nitride field effect transistors. So first we'll talk about the very conventional hard switch DC to DC converters. And those include the buck converter, as well as we'll talk about an emerging application for hard switch DC-DC conversion, and that's envelope tracking. Then we'll talk about the advantages of eGaN-FET in resonant DC to DC power conversion. And we'll do that by first taking a look at a traditional application, a 48 to 12 volt resonant bus converter, which is used in an intermediate bus architecture in a telecom or server application. And then again, we'll go and talk about an emerging application that's enabled by gallium nitride, and that's high frequency wireless power transfer. Looking at a hard switching waveform, we can determine what in-circuit or what device parameters can help improve the performance and give the best switching performance. Here's a traditional, theoretical, ideal turn-off switching waveform. What happens is when you want to turn off your device, you begin to lower your gate voltage, VGS shown in green. When the gate voltage is equal to your plateau voltage, your drain to source voltage, VDS shown in red, will start to rise, and that'll continue on until you reach your input voltage, VIN. The amount of time it takes to transition that voltage is determined by a variety of parameters, your input voltage, and the device parameter that really impacts the loss here is your QGD parameter, or your gate to drain or Miller charge. After you reach your input voltage, then you can transition your current to completely turn off the device. When your device goes to turn off, the device parameter that controls this turn-off time is your QGS2 charge. And that's your gate to source charge from the threshold voltage of the device to the plateau. So to improve the switching performance in a hard switching application, minimizing your QGD and QGS2 parameters will give you improved performance. Comparing 100-volt devices with eGaN-FETs versus state-of-the-art 100-volt Mosfet, you can see that the eGaN-FET offers around a 3 times reduction over the next best silicon Mosfet. And as you get away from the next best silicon Mosfet, that advantage increases. And what that's going to translate into is higher performance. What we've done here is we've run buck converters for a variety of input voltages ranging from 12 volts all the way up to 60 volts. And we've measured the efficiency at 1.2 volts out and 10 ampere. You can see that at the lower voltage, comparing 40 volt eGaN-FET to 40 volt silicon Mosfet, at around a 12 volt bus, we have a couple percentage points of efficiency improvement. As you increase that voltage, the switching loss will also increase, and the advantages offered by eGaN-FET will also begin to grow. So you can see going from 12 volts to 19 volts to 24 volts, the advantages offered by the eGaN-FET increase. And then when you switch to the higher voltage cases, we ran at 36 volts, 48 volts, and 60 volts. You need a higher voltage device. And as you go higher in voltage in device, you also have a general increase in switching charge. So as we showed previously, that 3x improvement of figure of merit over the state-of-the-art Mosfet, that's going to give us even larger switching advantages. So you can see going from low voltage to high voltage, GaN can offer performance improvements. And as you increase the voltage, you're going to see a larger advantage by switching to gallium nitride transistors. And these were all run at 500 kilohertz. looking at going to higher frequencies, you can also see that GaN offers even larger performance advantages. As we look to push to higher frequencies to give us higher power density, we're going to have a better switching transistor, and gallium nitride can provide that. You can see that looking at a 12-volt application, we have around a 3 percentage points improvement in efficiency. And when you go up to, say, a 60-volt input switching application, you have around a almost 15% improvement in efficiency when you compare gallium nitride devices to the best silicon devices today. So what we're going to talk about here is we want to talk about the point of load, and especially particular a low voltage point of load, which is very common, a 12-volt input application in server, telecom, in a variety of applications. So let's look at how GaN compares to silicon at lower voltages. As you can see, when you compare a 40-volt GaN device versus state-of-the-art 40-volt Mosfet, these are ones from Infineon, you can see that we have a significant advantage with regard to figure of merit. But for our 12-volt applications, oftentimes a 40-volt device isn't required. It's over voltage. And they can use something around a 25-volt MOSFET, 25 or 30 volts. What you can see is that the Gansett can offer a similar figure of merit to a much lower voltage rated MOSFET. And when you look at these applications, especially as we can continue to shrink the figures of merit and we continue to increase the switching speed, figure of merit isn't the only contributor to loss. We find that it's also very important to have a low parasitic package. And as Alex showed our devices earlier, we have a ultra-low parasitic chip scale packaging that's accomplished because we're a lateral device. All of our connections are on a single side of the device. Therefore, we don't have to have parasitic-ridden external connections that'll degrade our performance. And when you have low figure of merit, and when you have ultra-low package parasitic, it's also very important to optimize your layout to minimize the parasitics contributed by the printed circuit board. And at EPC, we developed an optimized layout to help further improve the performance achievable with eGansett. Shown in the upper left is the top view of the printed circuit board. What we have is, on the left side, we have our driver IC. On the top, we have our input capacitors. Then directly below it, we have our top device. Then we have our synchronous rectifier. To complete our high-frequency power loop, we start at the input terminal of the input capacitor, the input voltage node. It'll travel through the top device, then it'll travel down and travel through our synchronous rectifier, and then come back to a set of vias. And you can see that translates over to this side view. Then on the first inner layer, what we'll do is we'll bust down the vias, go to that first inner layer, and then we'll directly return the high frequency power loop underneath the top side power loop direction. What this gives us is it gives us an ultra low parasitic loop. It gives us the smallest physical loop size, and it also gives good field self-cancellation. If you want to look further into more details of how we achieve this design and how it improves over conventional designs, you can see our paper that's referenced here. But the idea with this is that we have an ultra-low profile self-canceling loop, and we can achieve total parasitic inductances, including input capacitance, the devices, as well as the PC board, under 400 picohenry. And that's significantly lower than even the best state-of-the-art trench MOSFET module, as we'll show in the next slide. So looking at how do we compare, looking at it, how does an eGansett compare to a state-of-the-art MOSFET with regard to efficiency in a 1 megahertz, 12-volt to 1.2 volt point-of-load buck converter? Looking at apples to apples, a 40-volt discrete GaN device versus a 40-volt discrete MOSFET device, you can see we can offer significant performance advantages, almost 3% at full load and around 7% at light load. And that has to do with a much lower figure of merit, a much lower package inductance in the device, and also a better PC board layout due to the low parasitic packaging capable of the device. Comparing to the lower voltage devices, you can see we had a similar figure of merit. We have, again, much lower parasitic, and that allows us to improve performance. So again, comparing a 40-volt EGAN VET versus a 25-volt discrete Mosfet, we can offer around a 2% full load improvement in efficiency and around a 3% at light load. And Mosfet manufacturers understand that they also need to improve their parasitic. So you're starting to see a migration towards the modules, the Dr. Mos and integrated modules to reduce the parasitic. So we also compared our 40-volt discrete-based GAN buck point-of-load converter to one of the best 30-volt integrated Mosfet modules. And you can see that, again, GAN can still significantly outperform all the way up to 20 ampere where we match load current. And again, the improvements are due to, we have a similar figure of merit. The improvements are due to the low package parasitic, low printed circuit board parasitic, and we're able to achieve lower parasitic than even the highest level of integrated trench Mosfet. And parasitics are not only important to efficiency, they're also important to things like EMI and over voltage ratings of the device. So when you look at the impact of parasitics on overshoot, what's shown here is the switching node waveform for the 12-volt buck converter at 20 ampere. The 40-volt GAN device compared to the 40-volt silicon device, we can switch around 5 times faster. And again, that's because of our lower figure of merit, our lower package parasitic, our lower layout parasitic. So we can switch around 5 times faster, and we can also significantly reduce the overshoot. When you look at an integrated silicon Mosfet module, you see as the Mosfet module goes lower in voltage, they can improve the figure of merit. But because of the high parasitics that are intrinsic in a two-sided trenched Mosfet device, even with the best integrated packaging, you're going to see that they're still not going to be able to get the inductances low enough to reduce the overshoot that comes with the high switching speed. Looking at a 40-volt based discrete Gansett design, we can offer similar or even slightly faster speed than a lower voltage silicon Mosfet module, and we can also significantly reduce the overshoot. And what that's going to allow us to do is it's going to allow us to further extend the usable range of our device. We're not pushing the limit of a 25-volt device at 12 volts like the silicon Mosfet, and we can actually push our 40-volt device safely up to around a 28-volt input bus. Shown here is a demo board that we have available where we have a 28-volt buck converter operating at 1 megahertz. We can transition 15 amperes of current and 28 volts in around 1.1 nanoseconds, and we only see around a 3-volt overshoot. So we can transition very fast, and we can transition with very low overshoots, and that's going to help with your EMI. It's also going to help increase the usable range of your device. We also understand that there's a lot of applications that want to look at higher voltages as well as higher currents. So we've shown the ability that we can parallel our devices to help push for higher current and as well as higher voltages. Here we have a 48-volt input buck converter. Using a single 48-volt device, we can push around 10 amperes of current out of it. Using 2 in parallel, we can push around 20 ampere. And then we've also demonstrated that we can effectively parallel 4 of our devices. So we have 8 total devices, and we can push 40 amperes out at 48 volts. So you can push a significant amount of power very efficiently and effectively by using these high-speed GAN devices. So those are some of the existing, well-known hard switching applications. And the ability of GaN devices to push their very high frequencies to give us these very fast switching speeds is going to help enable a new generation of technology. And one of those key areas that we see at EPC is envelope tracking, or ET. When you think of the cellular phone usage, when you go to a restaurant or go to dinner, look around and see how many people are on their cell phones. Ride on a bus or something like that. Everyone's always on their phone. Everyone's downloading videos, doing this or that. And the amount of data being used is going to grow significantly, and it's going to continue to grow. So to meet that demand for an increased desire and requirement for data, they're always trying to pack more information inside the signal. So when you look at going from on the left, a 3G wireless signal, all the way on the right, we have the new 4G LTE signal. You can see that the way that they're packing more information in is they're essentially using different techniques. And what they will induce is that it'll have a higher peak to average power ratio, or PAPR. So when you look at the 3G signal, the average power was only around half of the peak power. When you look at the 4G signal, the peak power is around 7 times what the average power is. And that's going to have a significant impact on the efficiency and the performance of the RF power amplifier. When you look at an RF power amplifier, it's traditionally driven with a standard DC bus voltage. And as the signal, and the RF power amplifier is the most efficient when it's driven very close to this DC bus voltage. Anytime it dips below it, generally that energy is dissipated as heat. So as you increase the peak to average power ratio, you're operating the RF power amplifier very ineffectively and very inefficiently. Essentially, you're operating well below the bus voltage for the majority of the time, and that energy in between the signal and the bus voltage is going to be dissipated as heat. The concept of envelope tracking is as opposed to having a fixed bus voltage, to have a power switching converter to track the envelope of the signal into the RF power amplifier. And that can significantly reduce the losses in the RF power amplifiers and significantly improve performance. Envelope tracking has been shown that it can double base station efficiency. So when we talk about point of load converters and fighting for a couple percentage points of efficiency, you see that the ability of GaN in these emerging applications to provide solutions that just weren't possible for silicon, where we can do things like double the efficiency, talking as opposed to a couple of a percent to 25 to 30%. So you can see the potential and the desire to use GaN inside these emerging applications. The way envelope tracking is done is there's a variety of topologies. But the general concept is you need a very fast switching buck converter. That envelope is moving very quickly. When you look at a 3 or 4G signal, around a 20 megahertz effective bandwidth is required to track that envelope. So that requires a very fast switching converter. And that's something that silicon-based solutions just aren't able to provide. So looking at one possible option shown here, is that there's a hybrid approach which uses a linear assisted buck. So what you have is you have a buck converter, and it handles a lower portion of the bandwidth and a higher portion of the power. And then the linear amplifier handles a lower portion of the power and the majority of the bandwidth. But again, you need a very fast switching buck converter to make these types of solutions viable. And GaN comes in, as Alex showed, we have a third generation, our EPC 8000 series, which is essentially targeting these ultra-high frequency applications. Here we show that we've operated these devices at a 42-volt input at 5 megahertz and 10 megahertz, and we achieve almost 90% efficiency, transitioning 42-volt input at 10 megahertz. So GaN devices can help enable these emerging applications by switching at very high voltages, very high frequencies, with very high efficiency, something that just isn't possible with the existing silicon technology today. Now we'll talk about the advantages of resonant and advantages of GaN and resonant and soft switching converters. So we just talked about the advantages in hard switching and how we can push the frequency. So then the idea is, well, why do we still need resonant and why do we still need soft switching? Well, we're always trying as power engineers to continue to push frequency so we can continue to push density. And resonant converters are still going to be very useful, very viable technologies, again, to push the frequency even higher than GaN can in hard switching applications. First, we'll take a look at a fairly well-known existing application. That's a resonant bus converter application. This is fairly popular in intermediate bus architectures and server and telecom applications. And the topology chosen for our example is shown here. What we do is we resonate the leakage inductance of the transformer with the small output capacitance, and that allows us to resonate our current and achieve zero current switching for our secondary devices, as well as limit the turn-off current seen in our primary devices. We also achieve zero voltage switching during the dead time by using the energy in the magnetizing inductance. In a soft switching application, the requirements of the switching transistor are much different than hard switching. In hard switching, we wanted to minimize our Miller charge, or QGD, and we wanted to minimize our current transition charge, or QGS2. Well, those losses are eliminated by techniques of zero voltage switching and zero current switching. But in soft switching and resonant applications, no longer are those the important parameters. Now we must focus on the parameters that induce loss in these topologies. And the key one is gate charge. Despite the resonant topologies, we still hard switch the gates almost always. So when you compare an eGansett versus state-of-the-art Mosfet for 40 volts, 100 volts, and 200 volts as shown here, you can see that GaN has a significant advantage. We have around a 3x advantage in gate charge times on resistance at 40 volts, around a 4x advantage at 100 volts, and a 6x advantage at 200 volts. So that's going to allow us to transition our gates much faster, as well as transition with much lower loss, which is critical in pushing to these much higher frequencies. Another important parameter for resonant and soft switching applications is output charge. Output charge isn't dissipated in the traditional manner of hard switching, again because of soft switching techniques like zero voltage switching. But to achieve soft switching, to achieve zero voltage switching, you have to displace that energy, that QoSS. So the amount of energy it requires you to displace that QoSS is going to determine how much circulating energy is required, and it's going to help having a lower output charge is going to help reduce your RMS current in these resonant and soft switching applications, giving you lower loss and better performance. So comparing Gansett versus a Mosfet, you can see at 40 volts, GaN offers around a 1.5 times improvement over state-of-the-art silicon Mosfet. At 100 volt, we have around a 1.6 times advantage. And at 200 volts, we have around a 2x advantage over the best silicon MOSFET available today. So to demonstrate the in-circuit performance advantages of eGansett versus silicon MOSFETs, we built two converters. When you look at overall performance in these type of brick designs, the transformer, the circuit board layout, they're very critical and they impact loss significantly, as well as the topology. So what we tried to do is we tried to create two identical circuits where the only thing we changed is the devices. You can see on the left we have the silicon MOSFET devices, and on the right we have our eGansets. The eGansets do their improved on resistance and versus area can help shrink the size. And what we can see is we have lower output charge and lower gate charge. The lower output charge is going to allow us to achieve our zero voltage switching transition in a much shorter duration of time. Compared to the Mosfet, which took around 87 nanoseconds to achieve zero voltage switching, the eGansett-based design can achieve zero voltage switching in around 42 nanoseconds. So that's going to help minimize your dead time and help reduce your circulating energy. What you can also see on the right-hand side is the gate drive images. You can see that the eGansett driven with a lower gate voltage can still transition much faster than the Mosfet. So that's going to give us, again, faster switching transitions, and it's also going to give us lower loss. When you put these advantages together in a high-frequency resonant converter, what it's going to give you is it's going to give you a longer power delivery period. And the longer you're delivering power and the less time you're circulating energy, setting up for your soft switching, the more efficient your design will be. The eGansett-based design, we can deliver power around 42% of each half cycle, while the Mosfet was limited by its high gate charge and high output charge to only around 34% for each half period. And that's going to translate directly into higher efficiency and lower power loss. So shown here on the left is the efficiency comparison of the eGansett-based design and Mosfet-based design at 1.2 megahertz. And you can see that the eGansett-based design offers around a 1% improvement throughout. And when you look at this, when you look on the right, that's going to allow us to deliver more power before we reach our thermal limit. So we can handle around 5 ampere more of output current for a 12-watt limited converter. And that's going to improve the power density of these systems. And it's going to help improve the performance in server and network and telecom applications. So to summarize the advantages of GaN and resonant and soft switching resonant and soft switching converters is that we can improve performance by minimizing two key parameters. We can lower the output charge and we can lower the gate charge. And that's going to give us more power delivery per cycle, and that's going to give us higher efficiency and lower conduction losses. Now we'll talk about how does GaN help enable emerging applications that require resonant or soft switching topologies. Wireless power is one of those emerging applications. No one likes to trip over cords, or how many times have you plugged your cord into the wall and it just hasn't been long enough? You picked up your laptop and yanked out the cord with it. Well, the idea of wireless power is very attractive because it gets rid of the wires. Imagine just putting your device down on the table and having it charge, or having it even charge in your pocket. eGansets can help enable higher efficiency in these applications, and they can allow us to operate at the higher frequency wireless power applications, like targeting the 6.78 megahertz and 13.56 megahertz. And these are essentially safer to the human body, as well as they allow us to have a longer distance wireless charging capability. And this is an emerging market, but it's estimated to grow significantly. It's anticipated it'll be around $10 billion by 2018, and at a growth rate around 42.6% a year. So taking eGansets, we created a wireless demonstration board. What you can see shown on the left is the source board, where we essentially have the switching power supply. Shown in the middle is the source coil and device coil, the wireless transmission, the transmitter and the receiver. And these were supplied by Electricity Corporation. And then on the far right, we have a device board, which mimics your handheld device with the electronic load that will be charged. To simplify the analysis, what we do is we'll basically simplify everywhere from the coil on to a simple resistive load. And that'll help us simply compare the topologies and allow us to compare the performance capability of each topology. One of the popular topologies in this type of application is the Class D amplifier. The Class D converter is highly resonant. You can see here we're resonating the voltage, we're resonating the current. Because of the resonance technique, you experience a very high voltage stress on the device, which is equal to around 3.56 of the input bus voltage, VDD. And the output charge is essentially absorbed into the matching network and it's part of the soft switching resonant transitions. Another topology, and one that we think there's a lot of promise in this type of wireless power transmission area, is a zero voltage mode class D. Zero voltage class D uses a more traditional soft switching technique, and it achieves VDS by using a zero voltage switching tank, and that'll transition the output voltage of the device similar to the resonant bus converter as shown. So by minimizing the output charge, or the COSS, we can allow for shorter dead time soft switching transitions, and it will give us higher available duty cycles, essentially give us longer power delivery periods. And that'll give us the highest system efficiency. When you look at the efficiency comparison of a variety of topologies, we compared a voltage mode class D design, we compared a current mode class D design, and we compared a single-ended class D, and then the zero voltage switching class D. You can see that the zero voltage switching class D offers the highest efficiency, followed by the single-ended class E. And the Gansets can again help enable the highest efficiency because at these high switching frequencies. This is at 6.78 megahertz, but it would also be true for 13.56 megahertz, another potential operating band for these wireless charging topologies. What you can see is that again, the zero voltage class D is the highest efficiency, followed by the single-ended class E. Another thing you need to worry about is the impact of the load. Depending on what you're charging, it's going to change that load impedance. And depending on the topology selected, the efficiency can be very dependent upon that load. When you look at the single-ended class D, as well as the current mode class D, they're highly resonant. And when you change the load, when you vary the load resistance, it has a large impact on the operating waveforms, and zero voltage switching and zero current switching can be lost. So as you can see, they can operate very efficiently at their optimal point, but as you get to lowering resistances for the class D and increase resistances for the current mode class D, the power loss is going to increase significantly, and that's going to require a heat sink. When you look at the zero voltage mode class D, it uses, again, a very traditional current source to achieve the zero voltage switching during the dead time, and that makes this topology very load insensitive and can give you good performance over a wide range of loads. So now we've discussed hard switching in traditional applications, emerging applications, as well as the advantages of GaN in resonant and soft switching applications. And now I'll pass it back to Alex, and he'll discuss where we're looking to go with GaN into the future.
All right. Thank you, David. So let's get back up here and take a look at the future. You know, in order to really see what the future is going to hold, you got to understand how much it costs. And for that, I prepared this table, which compares the cost of a gallium nitride transistor against a silicon Mosfet with the same non-resistance and voltage. And I'm going to compare it for 2013 and look into the future 2016. 2013, the GaN devices being 3 to 5 times smaller than their silicon counterparts, and since they're also built on the same starting material, a piece of silicon, the starting material costs are lower. The big problem is that when you grow that little crystal of gallium nitride, it's only a couple microns thick, but that is higher than the cost of growing a silicon epi as you would in a power MOSFET. But then you put these wafers into a wafer fab, and because we get so many more die per wafer, the wafer fab costs today are lower. There are also only about half as many wafer steps needed to make an eGaN FET as an advanced power MOSFET. Testing's the same. Assembly, we don't need a package. Our lateral GaN devices are self-passivated. They come in a chip scale format. When I was at International Rectifier, we used to build over 1 billion MOSFETs a quarter, and the cost of packaging was the same as the cost of the chip inside. So we start off with a 50% advantage right there. Now, overall, in 2013, the cost of an eGaN FET is somewhat higher than the cost of a power MOSFET. However, with increased volume and new advances in crystal growth that we've already input into our facilities in Taiwan, we believe that by 2016, we will actually have a substantial cost advantage over power MOSFETs. And that means that you'll get higher performance at a lower price. Where does this go into the future technologically? Well, for the last 4 years, we've been producing 40 to 200 volt parts on a Generation 1 and a Generation 2 technology. They're good up to about 500 megahertz, so a lot of applications with those. And in September, we launched a 3rd generation of parts. David talked a little bit about some of these applications in envelope tracking, for example. They are also at chip scale. They have gain up to 3 gigahertz. And they've now become our most popular products. We're also launching higher current devices very soon. Look for those by June, up to 45 amps, double the size of our current devices. We're going up to 600 volts later this year. And those devices will probably start off in the 5 amp range and go up from there, competing against IGBTs and cool MOSFETs. And then we're also integrating more functions onto a chip. Initially, you'll see devices in half-bridge and full-bridge formats, and then we'll start integrating some of the driver functions right onto the chip. That should open up very big markets and have a very substantial impact on the performance of the devices. And then finally, we're just at the beginning of learning how to use gallium nitride. You remember that efficiency curve way at the beginning compared against silicon? We're 1,000 times away from ideal theoretical limits in gallium nitride, and we intend to reap those benefits over the next few years by increasing the figure, or by improving the figure of merit by a factor of 2 year after year after year, much like Moore's law in integrated circuits. So in summary, eGaN FETs, they enable exciting new applications like wireless power and envelope tracking. They can replace power MOSFETs. In fact, we think they can crush power MOSFETs. They're very straightforward to use, but they're not just a drop-in for a MOSFET socket. So you need to put in some R&D, better get started today. And with that, let me take a few of these questions. Let's see, for those of you out there, we have about 3 minutes. I answered several of the questions all along the way, but I'm going to read some of the last few and try to answer them on the spot. It says, we have a serious issue with reverse current and high losses in the embedded diode. Any specific advice on that? David, can I turn that over to you?
Yeah. So when you look at, there's 2 ways to deal with the high dead time losses of the diode operation. One is you can minimize the dead time. While we have a larger forward drop than a MOSFET, we also have no reverse recovery. So if you do have a case where obviously looking to high frequency, whether it be MOSFET or whether it be GaN, minimizing the dead time is always going to be the most beneficial. If you can't minimize that dead time, we've effectively shown that you can parallel a Schottky diode with the device to minimize these dead time losses significantly. And if you go to our website, epc-co.com, we have literature where we explain how to minimize your dead time losses and how to select and where and how to place that Schottky diode if you're concerned about high losses during your off-state or third quadrant operation. but we can effectively reduce those dead time losses.
Thank you, David. The next question is about our package. It says it's the most optimized one in terms of spray elements, but it's still rather difficult to obtain reliable soldering results. Do you have any improvements in the near future? Well, one of the improvements is that we've been training. Contract manufacturers like Foxconn and J-Bill and all those, they now have the tools and techniques to reliably solder such a fine-pitch device. And I think over time, it'll just be experience. On our website, you can find several videos showing you how to solder these devices in an engineering environment. I think it's just a matter of experience, but we have high volume applications that are very successful. Next question is advantages of GaN compared to silicon carbide. I think that what we'll see is that gallium nitride devices will dominate the world under 600 volts, including 600 volts. And silicon carbide is more suited to vertical transistor applications in the 900 volt and above range. That's where I think the break point will be in the applicability of these parts. Gallium nitride is intrinsically more efficient as a lateral device, and silicon carbide is about equivalent to gallium nitride as a vertical device, but has several years head start in the technology. All right, let's see. There's one final question. May I know when is the module integrated eGaN FET coming out? I think that you'll see at APEC, if you visit us at APEC, we'll have some modules on display there. Also some other manufacturers are including our devices with their ICs in modules that should be launched at the end of 2014. But I think that's a very good product coming out very soon, a Dr. GaN kind of product. Let's see, Michael, do we have time for one more?
I think that's it for now.
All right. Well, thank you very much, and appreciate all of your time in this presentation.